All right. Hello, everybody. This video, we're going to find out what is the actual wave equation for quantum wave functions. So we can basically kind of sketch a pretty good, a little bit hand-wavy argument to get there, just given what we know about energy and writing out what that is and knowing a little bit about how we get a wave equation from, or a wave solution from a wave equation. So what do I mean by that? First, let's write down the energy for a non-relativistic particle. So we're going to develop a non-relativistic wave equation. We're going to say that the energy, and we're just going to say it's basically kinetic plus potential energy. So the total energy of a particle is kinetic energy plus potential energy. And we're just going to write that as kinetic energy, 1/2 mv squared, but we're going to write it, instead of 1/2 mv squared, we're going to use momentum. So we're going to write that as p squared over 2m. And potential energy, we're going to leave this term general, because what we're going to want to do eventually with this is just solve for all sorts of different cases of what this potential energy is. So right now, we want to leave this, I'm just going to write it as v, and it's going to be a function of position, but not generally time. It could be, in principle, be a function of time, and sometimes those are interesting problems, but for this course and at this point in this course, we're not going to consider the potential as a function of time. So we're just going to have, so that is our equation for the non-relativistic total energy of a particle. Now, if we combine this with the de Broglie relations, which, remember, we said that the wavelength is h over, let me erase that. Write that over here. Wavelength is h over p, and omega is e over h. Then let's see where this gets us. So I'm actually going to flip this around and substitute back in for E and energy and momentum. So where I have total energy here, I'm going to write h omega. Where I have p squared here, I'm going to write, I actually don't want to use wavelength, I want to use wave number instead. So remember that lambda is 2 pi lambda equals k. K is 2 pi over lambda. Let me write this out. Wave number is 2 pi over lambda. So what we have then here is that lambda is 2 pi over k, and so we can say that p, which is h over lambda, is hk over 2 pi. Remember, we had a shorthand way of writing h over 2 pi. We just call that h bar. So we just say momentum is h bar k. And actually, I messed up a little bit here. There's a 2 pi in here. E is h bar omega. So it's actually, this is frequency is e over h. But if we switch to omega, there's that factor of 2 pi in there. So sometimes forget about those factors. So over here, energy is h bar omega. P squared will be an h bar squared k squared over 2m. And then I'm going to leave the potential alone. And so this isn't there yet, but this is very suggestive, because this is starting to look like what we might get out of a differential equation for a wave. So if we let's leave aside the potential for the moment, and just look at these terms. And remember that if we don't have a potential, then we should have a freely propagating wave. If there's no potential energy, then if we just set something oscillating, it sort of keeps going. So we can kind of use that argument and say, well, if we want a solution that looks something like sine kx minus omega t, that somehow looks like a wave. Or at least has that behavior. That's not going to be the exact solution. We'll actually get to that. But it's going to have to be something similar to that, or some combination of that and something similar if it's going to act like a wave. That's what a wave is. If we look at this and say, well, what's the differential equation that gets us this thing in red? We've got our energy up here. We get a factor of omega by taking a derivative with respect to time. We get a factor of k by taking a derivative with respect to x. And so we get 2k's if we take two derivatives. And so that's sort of like the classical wave equation, but unlike the classical wave equation, instead of omega squared over here, we've just got omega. So this is suggestive, and it leads to this idea that, well, we've got some factors of h bar here too. And so this isn't really a derivation here that I'm doing. I'm not going to do the full derivation, but it's meant to suggest that I'm going to flip this around to reverse the orders of the terms. But the idea is we've got something that looks like a second derivative with respect to space. So actually, I'm going to write that h bar squared over 2m. And the convention here is that we have a minus sign. So let's not worry about that here. But derivative of our wave function with respect to x squared. I'll talk about the minus sign in a second. Plus, here we just have the potential times the wave function. And then equals, now we have this h bar omega term. How do we get h bar omega? We take one derivative with respect to time. But there's also going to be a bit of a wrinkle here. And that's the wrinkle is that our wave can be complex, and in fact has to be complex. And so what this is going to look like, again, there's some somewhat different conventions for how to write this, but we'll be consistent with the book here. I h bar, first derivative of the wave function with respect to time. That's supposed to be a t. So, like I said, this isn't really a derivation. I'm just trying to make it look reasonable. But this thing that I've written on the bottom here, this is the time-dependent, or the full time-dependent Schrödinger equation. So as Schrödinger was the one to first write it down, or the one to get credit for first writing it down. And it's the differential equation for a wave in quantum mechanics, just like the version we saw in classical mechanics. If we have a wave in a string, there's a differential equation there. You notice it's similar in some ways. It has two derivatives with respect to x, and something going on with time. What's new here is there's factors of h bars. That's to be sort of expected from that we're doing quantum mechanics. There's something interesting going on with like a minus sign or a factors of I. So that has to do with the complex nature of the wave function. We'll kind of come back to that. And also what's new here is not really special to quantum mechanics, is that's just that we're going to be very interested in the potential and how that affects the solutions. So that's what we're going to spend a lot of time on, but is basically this is our starting point, the time-dependent Schrödinger equation, and we're going to be solving it for different potentials and figuring out what that means for what a particle is actually doing.